Okay, today we'll begin topic 3 of exponential functions, modeling growth and decay. So what are some situations that can model exponential growth is today, and decay will be tomorrow. All right, so here is our growth model. So labeling the important stuff. So when a real life quantity increases, so we're doing increases today, that will be the plus here, by a fixed % each year, the amount in of the quantity after 2 years can be modeled by this equation. So looking at the equation, the A value is your starting number. So your starting amount. The R here is your rate. And usually the rate is given as a %, but you need to change it to a decimal. Time is usually in years. So T right here is your time, your exponent. Usually it's in years, but it can have some other time period. And then this whole thing right here, from graphing, we know this is your base. The whole base is called your growth factor. So what is it growing by? So the first couple of examples we're going to do involve using the table, and then we'll go to using a word problem to set up the equation. So in example 1, it says, in parts of the U.S., wolves are being introduced into the wilderness areas where they have become extinct. The population grew according to the table. So let's look at the table. All right, so what is the growth factor? So again, real quick, I'm going to write the model, A1 plus R to the T. The growth factor is going to be the base part, and the way that we find the base is we do the common ratio. So over here, if we divide the 60 by the 50, so we do bottom up. So we start at the bottom, 60 divided by 50, and we get 1.2. So from here to here, it's 1.2. And then we got to figure out the other ones. Now, because this is a word problem, it's an actual situation, these aren't going to be exactly the same, but they'll be pretty close. So if we divide all the other ones, I'm just going to do a few here. You can do the rest in your calculator. 50 divided by 41, we get approximately 1.21. That 9 is going to round it to 2. But again, the first part is pretty much the same as the other ones. So one more. If we do 41 divided by 35, we get 1.17, which again, if we were to make it go to the nearest whole number, so 1.17, or the one decimal place, that would round to 2 as well. So I'm just going to say the growth factor is 1.2. So this is going to be the base of our function here. This is the 1 plus R. So to find R, this part wants you to find the rate. To find R, you set the growth factor equal to the parenthesis part, 1 plus R, and you solve for R. So minus 1 minus 1. So this tells us that R equals 1.2 minus 1 is just 0.2. And we want to convert that to percentage. So if we multiply by 100, that's going to move the decimal place back twice, and it's a 20% rate of increase. So we're going to see the percent more on the next page where we do the word problems. All right, so if this pattern continues, we want to write an equation for the model. So we're going to have y equals, A was your starting amount. So how many did we start with? Right here is the first one. We started with 20 wolves. And then we multiply that by 1 plus R, And we already know the 1 plus r is the growth factor, which is 1.2. So 1.2, and we raise it to the x power, or a t in this case because it's time in years. So that would be our growth model. So to answer part C, we're going to use our equation. How long will it take for the wolf population to exceed 100? So this is talking about the population. So this is y. So we want to see what x value gives us the first number over 100. So we're going to take our calculator and we're going to put this into y1. 20 times 1.2 to the x. And we're going to look at the table to see when is the first time it reaches 100. So in the y equals, we want to put 20 times 1.2 to the, make sure you do the caret sign, and then you use x power. And then if you look at the table, the first time that it passes 100 is right here at 103. So we would say that the time takes, t is 9 years, because that's the first time that it's over 100. So that's how we're going to approximate the x value, is by looking at the table. Eventually, we will solve for it exactly, but we cannot do that until we have logarithms. So right now, we're just using the calculator. All right, moving on to example 2. Again, using the table, but this time we have to use the graph to generate the table. So the following graph represents the population of a certain kind of lizard. Right, so what we're trying to do is we're trying to figure out these y coordinates. So at 0, that's this point right here, but I got to figure out what these count by. So if this is 50, 1, 2, 3, 4, 5 in the middle, so 50 divided by 5 tells us that each tick mark is 10. 10, 20, 30, 40, 50. So it starts with 10. Now we can look at the rest of the table for 1, 2, 3, 4, 5, 6. So if we look at 1, it's at 20 because it's the second tick mark. If we look at 2, it's right there underneath 50, so it's 40. And we're going to establish a pattern. So once we establish the pattern, we can just use the pattern. So at 3, it's right here. So if I count 50, 60, 70, 80 would be that one. So if we try to figure out the pattern, because we're going to need that number, consecutively, what's happening from 1 to get to the next? We're multiplying by 2. Multiplying by 2. So we can just generate the rest of the table by multiplying by 2. And then we'll check to make sure that's correct. All right, so right here, 80 times 2 would be 160. 160 times 2 is 320. And 320 times 2 is 640. So checking that, it doesn't go to 6, but it goes to 5. So 5 is at the very top. So if that's 300, this would be 310, and 320 would be here. All right, so then we want to make an equation. Copy the equation down. Y equals a 1 plus r to the t. The y equals is your population. A is your starting number. So what number do we start with? We start with 10 lizards. And then we do times. We don't know the rate, but we know the whole growth factor. The growth factor, this whole thing, is what we're multiplying by. So we're multiplying by 2, and then we're going to raise that to the t power because time is in years. All right, so what is the population in 8 years? We could just continue our model, our table to get to 8 because there's only 2 more, or we can use the equation that we generated here. So if we wanted to use the equation, the 8 years, the 8 is giving us time. So we're going to plug this into the exponent for t. So equals 10 times 2 to the 8th power. And this I can just type straight into the calculator. I don't need to go to y equals because it wants the y value, not the x value. So let me pull up my calculator. And again, just doing, so from previously, in the calculator, 10 times 2 to the 8th was 2,560, would be the population after 8 years. So now going on to the next page. Now we have word problems that we're trying to generate an equation for and then use it to answer some questions. So I'm going to zoom out a little bit so I can see all of it in one problem. Right, so example number 3, in the last 12 years, an initial population of 38 buffalo in a state park grew about 7%. So first, is it growth or decay? Well, since it says it grew, I know that it's going to be a growth. And then we're going to use the formula from the previous page, y equals a times 1 plus r to the t, because it's a growth function. Tomorrow we'll do the decay. A value is your initial population, your starting amount. So it says the initial population was 38. So 38's here. And then the rate is 7%, but we don't want to put it as a percent into the equation, so we change it to a decimal by multiplying by 100. All that's going to do is move it over twice. So R is 0.07. So plugging it into the formula, we get A is 38. So 38 times 1 plus R is 0.07. And we don't know what time is for the model, so we just leave it as t. So adding those together, 38 times 1.07 to the t power. So this would be our growth factor if that's what it asks for. It's the entire base, but we really don't need that part here. For part B, it says use the model to estimate about how many buffalo were in the state park after 7 years. So the 7 here is giving us the time. So we're going to plug this in for t. So we take our equation that we made, 38 times 1.07, and we plug in 7 as the exponent. And then this one we just type in the calculator to get the y value. So 38 times 1.07 to the, we use the caret sign, and then 7 tells us that the decimal is 61.02. But we're talking about buffalo here, so we just round to the nearest whole number, and we say 61 buffalo. All right, and then the last part, part C, using the graphing calculator. So when it says that, I want to put it in the y equals. We're going to estimate the year when they were 53 buffalo. So in the y equals, y1 equals, we want to plug in our equation, not this one with the 7 in it. We want to plug in with the x. So we're going to do 38 times 1.07 and an exponent of x. So over here, we do y equals, oh, look, it's already there. 38 times 1.07 to the x power. And then we're looking at the table. You could use the graph too and estimate the 53, but looking at the table, if we come here, we want to see when the y first passes 53. So right here, 53 is that decimal, and I would estimate this to be 5. So t or x is 5 years. So at 5 years, that's when there's about 53 buffalo. Maybe not exactly, but about. All right, and then the last example, again, it's giving us the word problem. So we use the word problem to make the equation and then answer the questions at the bottom. So clear this, I'm going to need it. And clear this. Okay, in 1996, there were 2,000 573 computer viruses and other security incidents. During the next 7 years, the number of incidences increased by about 72% each year. I want to know first, is it growth or decay? So since it says it increased, we know it's growth. So then we do the equation for growth, y equals a times 1 plus r to the t. And then we got to find the other numbers here. So the a value was the starting amount. So in this year, they're started with 2,573 incidents or viruses. And r is the 92%. So as a decimal, it would be 0.92 because we move it back 2 places. So plugging everything in, a here, so y equals or n equals 2,573 times 1 plus r is the 0.92. And we raise it to the t power. You can make it as x if you want. It really doesn't matter. So then we add these together. So our equation is 2573 times 1.92 to the t. So we just add 1 plus 0.92. So about how many incidences were there in 2003? So here we want to figure out what t is. So if we're in 2003 and it started in 1999, how many years away, or 1996, sorry, how many years away is this? So from here to here, we would say we would just subtract 2003 minus 1996. Tells us that it was 7 years away. So that's what we're going to use for t is 7. So we just plug it in and we get 2573 times 1.92 to the 7th power. And then again here we just type it in the calculator and we round to the nearest whole number because we don't want decimals here. So 2573 times 1.92 to the 7th power. And we get, so I would erase the decimal part and we only want to write this part right here. 247,484. So 247,484 incidences. So all right, last one. Use the table to estimate the year when there were about 125,000 security incidences. So we take this number, and this is what we want y to be. So we're going to look at the y equals again. So in y equals, we plug in our equation, this one with the x in there, not the one with the 7. So 2573 times 1.92 to the x power. And we look at the table. We want to see when it gets above this. When's the first time it's above this? So just moving down. So this one is the first time it's above 125,000. So we want to say that t equals 6 years. So all we did was took the equation and put it into y1. And we saw when the first time it was above. All right, so those are growth models. Decay, we're going to do tomorrow. It's when it decreases or declines or anything like that, depreciates. But today, they're all growth functions. All right, so continuing our notes from yesterday, Unit 9, Topic 3, Growth and Decay. We did the growth parts yesterday, which were 12 and 13. And now we're on page 14 where the decay model's at. So a lot of these parts are going to be the same as they were yesterday. The only difference is now we have a subtraction. So looking at the different parts, we're going to label it again. So right here, the A value is your starting number. So we say that's your initial amount. The R is your rate. And again, usually it's given as a percent, but we need to change it to a decimal. The T is the time in years. And it's not going to ask us this time, but this one, like we talked about yesterday, is now called the decay factor, because it's going to be less than 1 since I'm subtracting it from 1. So you do this one when it says that it decreases, depreciates, declines. We're going to use this formula right here. So looking at our first example, it says a new television costs $1,200. The value of the television decreases by 21% each year. So here, is that all of it? I want to see all of it at the same time. So we need to first write out our formula. Okay, I'm not going to be able to see that bottom part, but we can move it. So we got to decide, is it growth or decay? So since it says that it decreases, then I know it's going to be a decay model. And I want the one above 1 minus R to the T. Your A value is what you start with. So the new TV costs $1,200. That's going to be the A here. And then the rate that it declines at or decreases at is 21%. So again, 21%. We want to move the decimal place back twice. So R is actually 0.21. So that's the number we plug in here for R. So if we set up the numbers, A for our equation is 1,200 times 1 minus the R. I'm going to put my T power, and R is 0.21. So if we subtract 1 minus 0.21, we get that the equation is 1,200 times 0.79 to the T. So we're going to use this equation for B, C, and D. So for part B, it says estimate the value after 2 years. The 2, since it's years, is giving us the time. So we're going to take our equation and we're going to plug it in for time. So 1,200 times 0.79 to the second power, so squared. So then we just type this one exactly into the calculator. So back on the calculator, we're going to go 1,200 times 0.79 to the second power. And we get that the cost is, this is cost $748.92. So this one I can actually round to 2 decimal places since we're dealing with money. All right, and then answering C and D, I'm going to go ahead and just copy the equations down there for C and D. So here it says estimate the value of the television, when the television will be $300. So taking our equation, we're going to plug it into y equals. So because 300 is giving us the y, we want to plug it into y equals and estimate the year. So we're going to do, what was the equation? 1,200 times 0.79 to the x power. And we want to see, when does x equal 300, or about 300? It's not going to be exactly 300. So on y equals, go ahead and type it in. 1,200 times 0.79 to the x power. Use x here, and you use the graph. So go until the number is below 300. So right here is when it starts getting under 300. So we would say that this one is 6 years. We will find more exactly once we learn how to solve, but right now we're just estimating. So estimate. All right, estimate the value after 15 years. So for this part, 15 is giving me time, which is the x. So here I'm going to plug in, but since I already have it in the calculator, I'm just going to go down to where x is 15 and see the price there. So when x is 15, y is $34.96. So this is money. Or you could have just plugged in 15 as the exponent. Now, as far as reasonableness goes, is this a reasonable amount for a TV? I mean, just because this is what it says mathematically, it might not be what happens in everyday life. So reasonably, probably not. Because after 15 years, the TV's probably broken, or it doesn't work, or there's new models out. So we say this one's not reasonable. Because this is so far. I mean, technology changes so quickly that in 15 years, the TV we have now is probably not going to work. Or, I mean, it's going to be a way better version. So it's not going to be worth anything at that point. So we call this extrapolation. So extrapolation is the process of estimating beyond the original data range. So usually with these exponentials, 10 years, going up to 10 years is getting pretty unreasonable. Sometimes it'll be okay. But usually we don't go that far. We don't go to 15 because then we get these prices that really don't mean anything. So this is subject to uncertainty. And a higher risk of meaningless results. So we can get it to a penny, but again, that's probably going to take 100 years, and at that point, it wouldn't. I mean, either be a classic because it's really, really old and really, really nice, or it's in the trash. So that's why we don't do the extrapolation.